Welcome to a brand new deep dive. And for anyone joining us today, our mission is to conquer what looks, at least at first glance, like an incredibly intimidating stack of handwritten theoretical physics notes.
Well, yeah, very intimidating.
Right. I mean, the document is literally titled Parametric Amplification in Magnetized Piezoelectric Semiconducting Plasma.
That title alone is, it's dense enough to make anyone's eyes just completely glaze over. It sounds like a random assortment of sci-fi buzzwords.
It really does. But if you are listening to this right now, do not worry. We are not going to sit here and just read pages of algebra and partial derivatives to you.
No, definitely not.
We aren't hosting a math quiz here.
Today.
The goal today is to extract the incredibly fascinating story that is buried inside all these derivations. We're going to figure out how physicists manipulate light, sound, and electrons inside solid materials.
Because the math we are looking at isn't just some abstract theory. These handwritten derivations are the exact blueprints for how modern technological components actually function. It is the literal language of physical reality being translated into actionable engineering.
Exactly. So imagine holding a small, solid, seemingly inert crystal in your hand. You shoot a wave of energy into it, like maybe a laser or a microwave.
Right.
Then, by applying a magnetic field and harnessing the invisible microscopic vibrations of the crystal itself, you somehow manage to amplify a completely separate signal.
Which is wild.
It sounds like magic. But what we have in front of us is the mathematical sheet music that proves this highly choreographed dance of energy actually works.
Yeah, and to understand how that amplification happens, we have to look at the environment where this microscopic dance takes place. The theoretical model defines the setting as a piezoelectric semiconductor.
Okay, so that first word, piezoelectric.
Yes, that is the physical foundation for literally everything that follows in these notes. In a piezoelectric material, mechanical stress and electrical charge are physically permanently linked.
So if you take the crystal lattice, which is just the rigid grid of atoms making up the solid, and you physically squish it or bend it, that deformation generates an electrical charge. It's the exact same physical mechanism inside those clicky grill lighters you use at a barbecue, right? You push the heavy button, tiny internal hammer strikes a piece of piezoelectric quartz. The mechanical stress creates a sudden electrical charge, and then boom, that spark ignites the gas.
That's a perfect example. And the thing is, that mechanical to electrical bridge runs in reverse, too. If you expose that exact same crystal to an electric field, it will physically change shape.
It actually flexes.
Right, it flexes. So our environment here is a responsive, flexible grid. But the second part of that definition we mentioned is semiconductor plasma. Now, when most people hear the word plasma, they automatically picture the surface of the sun or, glowing neon gas in a sign.
Yeah, but in solid-state physics, a plasma doesn't mean glowing hot gas at all. It simply refers to a mobile community of negative charge.
Spot on.
Inside this crystal, there is a sea of free-floating electrons that aren't tied down to any specific atom. They're essentially a fluid, moving freely through the pillars of the crystal lattice.
Which brings us to how we actually get the system moving, because to make this sea of electrons do something useful, we have to inject energy into the system.
Right. They won't just do it on their own.
Exactly. So the mathematical model introduces a pump wave, which is a powerful oscillating electric field that gets driven into the crystal, and a constant magnetic field pointing along a single axis.
And the physicist immediately sets up what they call a momentum transfer equation.
Yeah.
Instead of just listing out all the variables, if we look at what this equation is physically doing, it proves that the moment the pump wave hits the crystal, its energy transfers directly to those free electrons.
Yes.
The electric field of the pump wave just forces the electrons to start vibrating rapidly.
And that baseline vibration is categorized in the notes as the 0th order velocity. The electrons are essentially trapped in the rhythm of the incoming pump wave.
Okay, let's unpack this for a second. If I am picturing this plasma acting like a fluid inside the crystal, is this basically a microscopic mosh pit?
A mosh pit.
Yeah, the crystal lattice is the physical room. The pump wave is the heavy bass music making everyone in the crowd jump up and down.
Oh, I see where you're going.
But then, where does the magnetic field fit into that picture?
That's a great analogy. So the magnetic field alters the shape of the jumping. When a charged particle, like an electron, moves through a magnetic field, it experiences what we call the Lorentz force.
Okay.
This force doesn't push the electron faster or slower. Instead, it pushes it sideways, perpendicular to its path.
Oh, wow.
So in your mosh pit analogy, as the music makes the crowd jump, the magnetic field is this bizarre force constantly twisting everyone's shoulders, forcing them to curve as they move.
That curvature seems like it would create absolute chaos in there. I mean, if every electron is trying to vibrate to the pump wave, but the magnetic field is twisting their trajectories, they are going to start colliding in highly specific, localized ways, right? They're going to bunch up.
And that clustering is the entire point. But those curving clustering electrons aren't dancing in an empty void. They're moving through the crystal lattice.
Right.
And because of that piezoelectric property we established earlier, the physical floor of the room is about to react.
And this is where the notes introduce Poisson's equation.
Yeah.
For anyone who, hasn't taken advanced electrodynamics lately, Poisson's equation is essentially the mathematical tool that calculates how a localized clump of charge creates its own electric field.
Exactly. When those electrons get twisted by the magnetic field and bunch up together, they create a very strong localized pocket of negative charge. Poisson's equation dictates the strength of the electric field radiating from that specific cluster. And because they are sitting inside a piezoelectric crystal, that new localized electric field literally warps the physical grid of atoms beneath it.
So the floor of the mosh pit is literally sagging under the electrical weight of the clustered crowd.
Yeah, it's a great visual.
But the lattice doesn't just bend and passively stay bent. It has physical structure. It has tension. So as the crystal deforms, it wants to snap back.
Yes, it pushes against the electrons. It's a continuous tug of war.
That feedback loop seems to be the heart of the system. The mathematical model dedicates an entire page just to tracking every single physical force engaged in this tug of war.
It's incredibly thorough.
It accounts for the inertia of the electrons resisting a change in direction. It tracks convection, which in a solid-state fluid means calculating how the flow of electrons carries momentum from a crowded area to an empty area. And it also measures momentum damping.
Right, and momentum damping is essentially just the physics term for losing energy to friction, right?
Exactly. Every time an electron bumps into one of the rigid atomic pillars of the crystal, it loses a little bit of its kinetic energy.
It does. And factoring in all those forces, so the inertia, the convection, the frictional damping, the magnetic twisting, and the piezoelectric tug of war, it creates an incredibly dense block of calculus. We see these massive equations differentiating with respect to time over and over and over.
I have to admit, looking at the sheer length of these derivations, why do we need such monstrous math just to show that electrons are vibrating and a crystal is bending?
It looks like overkill, doesn't it?
It really does. If you and I wanted to calculate the force of a car hitting a wall, we could just use simple Newtonian physics. Force equals mass times acceleration.
Well,
why doesn't a simple equation like that work here?
Well, a simple equation fails entirely here because a Newtonian formula assumes a static relationship. In this crystal, we are dealing with a self-modifying feedback loop. The plasma pushes the lattice. The lattice reacts, generates its own electric field, and pushes the plasma right back. But by the time the lattice pushes back, the plasma has already moved to a new location.
Because it's being influenced by the twisting magnetic field and the original pump wave.
Precisely. You're trying to hit a target that is actively moving specifically because you are trying to hit it.
That sounds like a nightmare to calculate.
It is a challenge. The rigorous differentiation is the only way to isolate what the model calls the effective electric field. The mathematician is trying to determine how the baseline shaking of the electrons dictates the way these bunched up clusters, these density perturbations, travel through the crystal over time.
And the reason we need to know exactly how those clusters travel is because of what that feedback loop actually does to the incoming energy, right?
Exactly.
The original energy from the pump wave doesn't just stay intact. The continuous pushing and pulling between the electron fluid and the crystal lattice physically fractures the wave. The model actually defines this as perturbation splitting.
Yeah, when you look closely at the derivations for the clustered electron density, the variable cleanly splits into two distinct mathematical identities. The notes label them a fast-varying part and a slow-varying part.
The fast-varying part represents an electromagnetic wave. It's essentially a scattered light wave moving incredibly fast through the material.
Right.
But the slow-varying part is identified as an acoustic phonon wave. Now, an acoustic phonon is literally a sound wave. It is a mechanical vibration physically rippling through the atomic structure of the solid. So the electrical energy from our pump wave has split into a wave of light and a wave of sound.
Which is amazing. That physical split happens because of the dual nature of the piezoelectric environment. The electrical side sustains the electromagnetic light wave, and the mechanical side sustains the acoustic sound wave.
It's acting as a bridge.
Yes, but just having the energy split into light and sound doesn't automatically mean we have a working amplifier. If those waves are just bouncing around randomly, all you get is microscopic noise.
Right, just static.
Yeah.
So to turn that noise into amplification, the theoretical model introduces a strict physical requirement called phase matching.
Crucial concept.
The math insists that the frequencies of these waves must perfectly align. The frequency of the incoming pump wave must equal the frequency of the scattered light wave plus the frequency of the sound wave. Their momentum vectors have to sum up perfectly too.
Because phase matching is really just the strict enforcement of the fundamental laws of conservation of energy and momentum, but applied to wave dynamics.
So if we go back to the idea of a rhythm, is phase matching basically the universe's strictest game of three-way jump rope?
Oh, I like that.
You have three distinct entities turning at once. If the fast light wave, the slow sound wave, and the massive pump wave aren't perfectly synchronized, the ropes just tangle.
The absolute tangle.
The energy sloshes backward or dissipates into heat, and the whole amplification process just trips and falls apart.
That jump rope visual perfectly captures the stakes of the physics here. If the rhythms are misaligned, the transfer in energy is destructive. But if the phase matching conditions are met, if the turners are in perfect sync, energy flows continuously and stably from the high-energy pump wave, cascading down to simultaneously feed the acoustic sound wave and the scattered light wave.
So the smaller waves literally siphon energy off the bigger wave to grow stronger.
Exactly.
And that is the very definition of parametric amplification.
Right. And to prove that steady siphoning mathematically, the notes utilize a technique known as the rotating wave approximation.
Now, what does that approximation actually do for the physicist who is sitting there trying to solve this by hand?
Well, when you have multiple waves interacting, the mathematics naturally generates a lot of hyper-fast oscillating terms. These terms vibrate so quickly that over a measurable period of time, they essentially average out to zero. They don't contribute to the steady one-way transfer of energy. So the rotating wave approximation allows the physicist to surgically remove those irrelevant high-frequency terms from the equation entirely.
Oh, so it's like taking a photograph of a busy street with a long exposure.
Yes.
All the fast-moving cars just blur out and disappear, and you are left only with the solid, unmoving architecture. The approximation lets the physicist blur out the mathematical noise so they can focus entirely on how the massive pump wave couples directly with the slow acoustic sound wave.
Which is absolutely vital, because at this point we are approaching the ultimate destination of this theoretical model. We understand how the waves mix. We understand how the energy transfers from the pump wave to the signal wave.
Right.
But an engineer can't build a device based purely on a concept. They need to measure exactly how good the specific piece of piezoelectric material is at executing the process.
And this is where the mathematical heavy lifting changes domains. Up to this point in the notes, all the derivations have been tracking changes over time.
Yeah.
But to find the crystal's ultimate score, the mathematician shifts into the Fourier domain.
Right. And for anyone wondering why a mathematician would suddenly switch mathematical domains halfway through a proof, it's all about finding the right perspective.
Yeah.
Working in the time domain is like watching a waveform on an oscilloscope, trying to track every single peak and valley as the clock ticks. It's tedious.
Moving to the Fourier domain is like looking at the graphic equalizer on a stereo. Instead of watching the raw sound wave wiggle over time, the Fourier transform breaks the complex wave down into its individual frequencies.
Exactly.
It lets you see exactly how much bass, mid, and treble you have simultaneously. It just makes analyzing specific frequencies infinitely easier.
And once we're in the Fourier domain, the model proves something really crucial. The amplitude of the slow acoustic wave is directly dependent on the square of the incoming pump field.
And squaring that variable is a massive detail. It means the relationship is nonlinear.
Yes.
If you slightly increase the intensity of the laser or microwave you are firing into the crystal, you don't just get a slight increase in amplification, you get an exponential spike.
That nonlinear relationship drives the entire final section of the derivations. The physicist's goal here is to calculate the induced polarization. In a solid crystal, when an electric field passes through, it literally pulls the negatively charged electron clouds slightly away from their positively charged atomic nuclei.
So it shifts the internal balance of the atoms,
Yeah.
basically churning the entire crystal into a macroscopic pulsating dipole.
Exactly. That temporary electrically induced shifting is the polarization. And calculating how effectively the material achieves that polarization under the influence of three mixing waves leads to the final master symbol, A sub En. That's the nonlinear optical susceptibility.
The final pages are a meticulous, honestly kind of agonizing algebraic cleanup just to isolate this exact variable. The physicist carefully separates the massive equation for chi sub En into its real parts and its imaginary parts.
Right.
The imaginary parts relate to energy absorption, but the real part is what we actually care about for amplification.
And the resulting expression for the real part of chi sub En factors in every single physical reality we've discussed today. It includes the acoustic damping of the crystal, the baseline plasma frequencies of the electron sea, and the twisting effects of the external magnetic field.
So from a practical standpoint, if I'm an engineer looking to build a signal amplifier for a satellite or maybe a quantum computer, that final susceptibility score is everything. It's basically the horsepower rating of the crystal.
It is. It is the defining quantitative metric of the material's capacity to act as a wave mixer. But the true value of that massive equation isn't just giving you a static score, it provides the exact knobs and dials.
Oh, because the variables are laid out so clearly.
Yes. The engineer can look at the math and realize that by tuning the strength of the external magnetic field, or by tweaking the intensity of the incoming pump wave, they can dynamically control the level of amplification.
They aren't stuck with whatever properties the rock naturally has. They can actively pilot the crystal.
It transforms a rigid piece of solid-state matter into an adjustable, highly tunable technological machine.
Pulling this entire journey together is just staggering. I mean, we started with a piezoelectric crystal filled with a fluid sea of free electrons. We injected a massive pump wave into it while applying a twisting magnetic field.
And that forced the rigid crystal lattice and the fluid electrons into that relentless tug-of-war feedback loop.
Right, and that violent interaction physically fractured the energy into electromagnetic light and mechanical sound.
And by strictly enforcing the universal rhythm of phase matching, we traced the mathematical proof of how to siphon energy from the pump to amplify those waves. We arrived at the exact mathematical dials needed to control a solid-state amplifier.
It is a profound synthesis. It seamlessly combines fluid mechanics, electrodynamics, and solid-state physics into a single cohesive proof.
It really is.
But before we wrap up today, there is one buried detail in these notes that fundamentally reframes everything we just learned.
Ooh, there's usually a catch in models this complex. What caught your eye?
Towards the very end of the complex algebra, right as they are calculating the velocity of the electrons to finalize that susceptibility score, the physicist writes down a crucial assumption.
Okay.
It reads, and I'm quoting here, assuming weak B0 is approximately 0, so the cyclotron frequency approaches 0.
Ah, the weak magnetic field assumption.
Yes. They explicitly assume that the external magnetic field is relatively weak, and they do this purely to make the monstrous math solvable by hand.
Right, because if the magnetic field gets too strong, the cyclotron frequency, which is how fast the electrons spin in circles, becomes too dominant.
Exactly. And the equation becomes mathematically impossible to close neatly. They nerfed the magnetic field just so they could cross the finish line.
Well, in theoretical physics, assumptions are often required just to build a foundational functional model. You have to simplify things to prove the baseline concept. But you're pointing out that the physical world isn't actually obligated to play by our simplified rules.
Exactly. Which raises a terrifying and exciting question. What happens if the magnetic field isn't weak? What if an experimental physicist takes this exact piezoelectric crystal, blasts it with the pump wave, but then cranks the magnetic field up to absolute extreme levels?
The twisting Lorentz force would completely overwhelm the standard collision rates.
Right. So does this elegant, highly synchronized jump rope model just shatter? Does the amplification fail? Or, and this is what's crazy to think about, does pushing a nonlinear system into extreme conditions unlock some entirely new, chaotic, highly complex form of wave amplification that our polite, simplified math can't even predict yet?
That's a fascinating thought.
Are we just scratching the surface of what these materials can do simply because our current calculus equations are too polite to handle the truth?
When you introduce extreme variables into a feedback loop, that sensitive, polite physics is usually the first casualty. The result would be entirely uncharted territory.
Definitely something to ponder the next time you hold your smartphone or look at a piece of modern hardware. Beneath that sleek glass and plastic, there is a chaotic, microscopic mosh pit of energy, playing by a set of rules we are still just beginning to truly comprehend.